Okay, so we're going to look at two applications of uniform circular motion. Okay, the first one these will both be kind of a combination of uniform circular motion and friction. Okay, so the first one we're going to do is, let's say that you're on a bicycle and you're going around a turn. So we're going to look at an overhead view. So if this is a road and here's a bicycle, alright, you can kind of see the bicycle like overhead view. It's a kind of an abstract bicycle, so because you can see all like the sides of it at the same time. Anyway, the bicycle wants to go in a straight line, but we're turning it. So the natural tendency of the bike is to keep going like this. It wants to keep going straight, and some force is causing it to go inward on this turn. Okay? And so that imbalance of forces that causes its direction to change in a circle is called the centripetal force, okay, which is mv squared over r. And no matter the circumstance, if something is rotating, then the forces add up to be equal to mv squared over r. Okay, and so in this case, those forces are going to add to be mv squared over r, and the only force causing it to happen would be the friction between the bike and the ground. So if we do a free body diagram, the bike has weight, and it has a normal force, and then it's got this frictional force, in this case static friction actually, that's kind of pushing it in a circle. It's causing it to go around. It's continuously pushing into the center. That's static friction. So we say mv squared over r is equal to static friction. We could even say, well, static friction is equal to the coefficient of friction times the normal force. So this would be equal to, normal force is going to be equal to weight in this case. This would be equal to mu times mg. Okay, and then you could solve for mu here if you want. There's lots of ways that you could handle this equation from here, or things that you could do with it. We could solve for coefficient of friction. We could say if the coefficient of friction is this, how fast could the bike take this turn? Things like that. Okay, so this is one application of forces in combination with Newton's Newton's laws. Alright, so we'll look at two more problems here. The next one we'll look at is, let's say you're going to do like a loop. Okay, so if you're going to go on a bike, and let's say the loop has a radius of 5 meters, and so the question is, how fast do you have to be going in order to make it through this 5-meter radius loop on your bike? Okay, well, we can do a net force, or a free body diagram for at the top here. So at the top of the circle, we have gravity pulling downward, the weight, and then at this moment, there's also normal force pushing down. Okay? And so we're going to write a net force equation for this. So the sum of the forces acting in the direction of the radius will add to be mv squared over r, because we're in circular motion. We're going in a circle, so mv squared over r. Okay? And so acting downward, remember, towards the center is positive. So we have positive weight, mg, and positive normal force. Okay? And so, in this example, it says, how fast do you have to be going at the top up here so that you can make it through the loop? Well, let's think about it like this. Your weight is constant in this situation. So no matter how fast you're going, the weight doesn't change. However, this quantity here, the centripetal force, has to increase when your velocity increases. So the faster you go, the more force you need to keep you in a circle. And the slower you go, the less force you need to be in the circle. Okay? And so if you think about it like this, then at the moment that you're going, if you're going the minimum speed to make it through the circle, at the top right here, you're just about to fall because you're going just almost too slow. Which means that this loop here doesn't have to help push you in the circle because gravity's doing all the work. Okay, so at that moment where you're about to fall out of the circle, the normal force is 0. Because if v is any less than that, then the weight is stronger than this required centripetal force to make you rotate, and you're just going to fall. Okay? And so we could solve this. We could say, okay, if this is equal to 0, then mv squared over r equal to mg. These m's will cancel out. V is going to be equal to the square root of g times r, which in this case is about, so this would be like 10 times 5, which is like 50. So V would be about 7 meters per second. So in this particular loop, the bike would have to be going 7 meters per second at the top of the loop here in order to make it in a circle. Okay, later when we talk about energy, you could actually figure out how fast the bike would have to be going down here in order to be going 7 meters per second at the top of the circle. Okay, so this is another application. And then we'll look at one more example here. And have in this example here, we're going to look at when, so like there's this amusement park ride where you spin in a circle and you get stuck to the wall because you're spinning so fast. Okay, and in this case, there's 3 forces acting on you. You have the weight pulling you down, and in this case, normal force is pushing you inward because normal force is always perpendicular to the surface. And then the reason you don't slide down is because friction is holding you in place. Okay? So if we were to look at an overhead view, if this is the person right here, they want to keep going in a straight line, but the wall is forcing them inward. So there's a normal force right here forcing them in a circle. Okay? And so because of that, you feel like your body's getting pushed outside, but really the reason why is because your body is trying to go in a straight line and it's getting pushed inward. Okay, so we can find here the amount of, maybe like the, let's find the coefficient of friction required to make this work. Let's say that, or let's just solve for the amount of static friction. Okay, let's say that this circle has a radius of 10 meters, and then you have a velocity of, let's say your velocity is maybe 7 meters per second. Okay, and so in this case, we can say, well, you're in rotation, so the sum of the forces in the direction of the radius have to be equal to mv squared over r. And in this case, the only force acting in the direction of the radius is the normal force. We'll say it's positive because inward is positive. Okay, and then actually, yeah, let's solve for coefficient of friction. So if we want to find coefficient of friction, we're going to have to do a net force equation for y, and this will add to be 0 because they're balanced. So 0 equals, we'll say up is positive, so static friction minus the weight mg. Now remember, static friction, this tells us that static friction is equal to the weight mg. So remember, static friction is also equal to mu times the normal force. So in this case, since the normal force is mv squared over r, then we'll say mu times mv squared over r is equal to m times g. Now the m's are going to drop out because they're on both sides. And so we can get that mu will be equal to, we'll multiply r over g times r divided by v squared. So v is 49, or v is 7, so v squared is 49. So this would be mu is equal to 10 times 10, which is 100, over 49, which means that mu is about 2, which is pretty large for coefficient of friction. So this is probably an unrealistic question. Okay, so this is another application though. Hopefully this is kind of making sense. Again, we'll keep working on this in class.